Okay, everybody, so let's take a look at a simulator that's going to play games 1 and games 2 for us as many times as we need to see it until we really understand what's going on with the games themselves. So here you see game 1, and then you see 10 results, just like you did when you had to roll your die 10 times. So this person won 1, 2, 5, 3, 5, 6, 2, 3, 5, 2. And you might be asking yourself, where are the dice here in Excel? Well, they're down here. There's a great little command called rand between that generates a random number between any two values, which is exactly how you simulate a die using Excel. So rand between 1 through 6. And you might notice exactly that the number here matches the number here, because that's the way game number 1 works. On average, this particular game won 3.4 pieces per game over those 10 games. All right, game number 2. Oh, this poor person here. Wow, this is terrible. They lost 15 3 times. You can see why. They rolled 1 3 times down here. They got a 6 here, which means they got their doubled 6 to get 12, but they didn't make up enough points on other rolls to get their average any larger than 0.7. So clearly, game number 1 was better than game number 2 for these 10 rolls. But let's roll again. There's a new roll, a new set of rolls. And you can see they're very similar to the previous ones. Like, for example, there's a negative 15 here in game number 2. But since we got so many 6s and 5s, we were able to bump the average up to 5.3, which is much better than the 3.6 average over here. Let's roll again. Okay, now 3.4 is the average for game 1, 4.5 is the average for game 2, and so forth. And we can keep doing this all day long. Oh, there's another terrible game for game number 2, and a slightly better one for game number 1. Another bad, well, I shouldn't say bad, a worse game for game number 2 than game number 1. Same here, same here. Oh, whoa, man, 8.8. Lots of big rolls there. But here's the deal. We can do this all day long, and we can react by going, whoa, all day long. And it's even possible sometimes to have a negative average for game number 2. It's kind of, oh, there's one right there. If you roll enough 1s in the 10, you're going to end up with a negative average, because even though you won candy back, you're not countering it with the larger rolls on the other side. And this is great, except it's not, because we can't keep track of game after game after game. We can only look at 10 games at a time. So what I've done here is I've set up this spreadsheet over here. Now this is going to be a little bit confusing at first. So let me zoom in here and tell you what we're looking at. These results here are exactly the same results as they were on the previous sheet. So for example, right now you might remember there was a negative 0.6 candies per game over the 10 games from the previous sheet. And there were 4.5 candies per game before that. But what you're seeing down here are the actual averages of all the games we have played so far. So remember when I said earlier, this is great, except we're only seeing 10 games at a time? The Excel spreadsheet right now is actually seeing everything. I'm keeping track of it behind this chart, which we'll refer to a little bit later. So every time I press F9, we get new data up here, but the data down here updates and keeps track of all the cumulative data. So what we're going to do is I'm going to go ahead and let this thing randomize for a good long time. And we'll speed the video up here in a second. And then we'll see where it takes us after a few 100,000 rolls or so. I think it's stabilized enough. It's fighting a little bit here and there, but it's stabilized now. And when I say stabilized, what I'm really looking at are a couple different things. First of all, I was looking at these graphs as they were generating. And we're going to talk more about these graphs in the next couple questions of the lab. So I don't want to say too much about them, but they really stopped bouncing around a whole lot. They kind of stabilized in the fact that they were changing a little bit here and there, but not changing a whole lot. Also, the averages here weren't changing all that much. 3.5 would bounce up to 3.6 sometimes, back down to 3.4, but it seemed to like being at 3.5 for game number 1. And for game number 2,
it would bounce up to 4.3 down to 4.1, but it seemed to like being at 4.2. So it sure looks like after a few thousand rolls of these dice that the average for game number 1 is 3.5 and the average for game number 2 is 4.2, which is actually kind of interesting and telling if you think about it, because game number 1, as we talked about earlier, you can't lose playing game number 1. But over a long period of time, it appears that game number 2 is actually better. One last thing to chat about with respect to, actually 2 last things to chat about with respect to this. While the game was playing, I mentioned earlier, these were the die rolls that were happening. So every time I press F9, you get new dice. Every time you re-randomize. Oh, sorry about that. 0.1. I was actually keeping track over here of how many of each of the numbers on each of the dice came up. And you might notice something special about these numbers as I'm going to try to re-randomize them here. As I'm holding down this F9 button, they're not moving a whole lot. You can see them changing a little bit here and there. That's because the dice are rolling about 16.666666% of the time. And you might ask me, like, wait a minute, what do you mean by 16.66666% of the time? We have to remember, the reason dice are used is because it's an equal chance of rolling any one of the 6 sides. 1 out of 6. If you change it to a fraction and then divide the 6 into the 1, you end up with 16.6666666 repeating. So that is why these pie charts appear to be evenly sliced. You're getting about 1/6 of each. As I was chatting, you might have even noticed that these 2 blue slices, which represent the number of 5s, it looks like, this one was at 17.2, I believe, when we started, and this one was above 17 as well, and they're both falling. Because as time goes by, the dice are going to even out. And eventually, they'll all stabilize out. If we were to sit here for days and days and days, they would all stabilize out to 16.66666. Okay, that's one thing. The other thing too, and you'll come back to this in the lab when you do the last couple questions or the middle couple questions. I'm keeping track of percentages of things that happened for each game. So for example, if you look at the green bars right here, this one says 16%. That one says 64%. Taken together, 64% plus 16% is 80%. If you add 80% to 19%, you get 99%. Now, those bars should add up to 100%. So why don't they? And the answer is maybe not satisfying, but very, very simple. These are rounded off values. They're not exact. They're rounded off. Anybody notice there's a little tiny bar right here? There's a little tiny bar right here. That bar right there represents a very, very special thing that happened during the playing of game number 1. And it didn't happen very often. It maybe only happened one time. There was one time when game number 1 rolled a lot of 6s. I didn't see it go by. It went by very, very quickly while I was holding down this F9 button. But you see how it says 0% right there? It's not really 0%. If we were to make the decimals have more precision, we would see that something happened there. You can tell there's a little tiny bar right there where there isn't one here or here or here. So the fact that these numbers don't add up to exactly 100% is actually nothing to be worried about. They do, and as a matter of fact, I didn't even see this one over here. Did that one just happen? I didn't happen to notice that one. There's one there now too. So these would add to 100% if we had the full rounding abilities available to us. But that's game number 1, light green right here. If you look at game number 2, dark green, let's do some quick additions here. 6% plus 7% is 13%. Plus 8% is 21%. Plus 14% is 35. Plus 14 more is 49, plus 15 more is 64, plus 12 more is 76, plus 8 more is 84, plus 6 more is 90, plus 2 more is 92. Now, 92 is not very close to 100%. It's pretty clear that this 99 point whatever it is really, really close to 100%. But 92, that's 8% away. Where could 8% possibly be? Now, I'm going to pose that question here, and I'm going to offer it as an extra credit in the actual lab you're working on. Okay? But I think you have everything you need right now to answer the questions for the simulator part of the lab. So let's get back to it.